Hello, welcome back. This is the last video in this series of radiation detectors, and the topic is film. So this is something you're probably familiar with at a cursory level, at least even in a popular imagination. We see things about X-ray films. You'll see the doctor sticking a film on the light box and making the miraculous diagnosis. But do we understand how they work? Yeah, most of us do not. But after this video, you will. So here we go. So for radiotherapy applications, we actually have two types of film: radiographic film and then radiochromic film. And they're different, and I'm going to go through them separately. I'm going to start with radiographic film because it's kind of similar to what you might know, the traditional old photographic film. All of these films have some layer, active layer, that's several microns thick. If I zoom in to that layer, what I would see here are these little crystals in radiographic film, and these have inside them some silver crystals. Typically it's silver bromide or silver iodine. And then what happens is if an electron comes in, that's what you're gonna measure the dose. It has a redox reaction that then puts the silver on the surface, and then that's something that you can read out as a darkness in image. That's the latent image that then gets read out in a processor through some chemical reactions, right? So radiographic film has several advantages. The number one thing is that it's high resolution. It's basically, photographic level resolution, so much higher than anything we've been talking about up until now. But that comes also with some disadvantages. So one is the processor that's needed to pull that latent image out. There's a lot of chemicals, a lot of materials. There are some other disadvantages. But let me just describe how you would pull out a dose from these films. And this is true of all the films. So you have some light coming in with some intensity I, 0, and then light coming out with some intensity I. And so you're basically looking at how much does the film absorb that light. So, and the term for that is called optical density, or OD, we call it. And so let's write out the formula for optical density. It's actually defined as the logarithm, base 10, of the ratio of those intensities, intensity in to intensity out. Sort of like an exponential function. And then I can plot that. If I plot optical density versus dose, there's a very important curve here. So it's number one, it's not linear. It doesn't follow a line. Okay, it has a special shape. So it might start here at 0.2. That might be a typical value. If you have 0 dose, there's some baseline fog level, and then it comes up and it saturates. So it might saturate at an OD of 1. That saturation depends on the speed of the film and so on. Oh, by the way, you plot logarithm of dose here usually. And so this is the very typical curve. It's called the H&D curve. That's for Herder and Driffield, who characterized this in the late 1800s. So here's another effect with these radiographic films, is that there's an energy dependence of the film response. So this is from TG69. Here's a high energy beam, and over here in blue, let's say, is a low energy beam. And you'll see that for a given dose, the optical density is going to be very, very different. So there's a couple implications to this. One is if you calibrated it in a high energy beam, you would not want to use that same calibration to measure a low energy beam. Two is that if the spectrum of a beam changes in different locations, for example, say by field size or depth, then the response may be different in a single film. So you really need to be aware of this. All right, so let me add to this list. You'll need a scanner to process radiographic film, and also there's this energy dependence that I talked about. So that's kind of the list of issues around that. So now let's go over and look at radiochromic film. Sometimes you'll see this referred to as GAF chromic film, or EBT. Those are trademark names, so I'm going to stick to the more generic name of radiochromic. So the idea with radiochromic film is the same as it was with radiographic. You want to get sort of a dose-dependent darkening of the film, but the mechanism is different. So in radiochromic film, you have these monomers, small molecules. They're diacetylene molecules, and they're embedded in a thin plastic, typically a few tens of microns thick, that sits on a substrate. And then you have a reaction that happens when radiation comes in. So here, if you have a charge or an electron, there's a cross-linking of these monomers. So like that. And the result of that cross-linking is that it becomes optically opaque. So the film darkens. So there are several key advantages here. So there's no processor needed. It happens naturally. You can leave it out in room light. There's a little bit of light sensitivity if you leave it out, but you don't need a chemical or a darkroom. It has a high resolution, just like radiographic film. It's photographic kind of resolution. There's very little energy dependence for radiochromic film. So that's one of the key differences between these two films. In this one, you also need a scanner. And actually, the protocol to turn the opacity into dose is a little more complex. So here's how you might use this. So what you'll see here on the left is a treatment plan dose distribution. And then in the middle, this is the dose distribution measured on a film, on a radiochromic film. And then you can compare these dose distributions and see how close they are to what you expected. And we'll come back to this in the QA video. All right, those are the basics of film. I'll leave you with a little bit of further reading. It's quite a complex technology, and a lot can be said about it, but these are the basics. There are many applications for this, and I really didn't get too much into the applications, but we'll see that a little more as the course goes on. Thank you.